Yeah, in this video, I'm going to discuss about the chemical reactivity of alkynes, which is pulled out from the degree first semester syllabus, that is Acyclic hydrocarbons chapter 5. The whole chapter has been discussed on my YouTube channel, and the details of this has been given in the description box below. So you can go through that. Let's look at the chemical properties of alkynes now. In my previous video, I've already discussed about these physical properties and the acidity and the preparation of alkynes. Now, let's see these chemical properties. So, this alkynes, we know that it is a C triple bond C. It is having a triple bond. So, because of this presence of one is sigma bond and the other two are pi bonds, because of the presence of these two pi bonds, so it's electron rich, so it acts as a nucleophile, so it can attack the electrophile, so it undergoes electrophilic reactions and the addition reactions. Because of this presence of pi bond here, it undergoes the addition reactions easily. So because it's electron rich and because of this presence of this pi bond, it can undergo this electrophilic addition reactions as similar to that of these alkenes here. So the the main reactions it undergoes is addition of the halogens, hydrogen halides, that is HX, and water in the same way as the alkenes are undergoing these addition reactions. So in alkenes, only one molecule of this reactant is necessary, but here, because of the presence of two bonds here, I mean two pi bonds, these additions, two molecules of the reagents can be added to this C triple bond C. Let's look at this addition of the halogen now to this alkynes, that is C triple bond C, and these alkynes are less reactive than alkenes. This is alkenes. Why? Because here during the mechanism, this bromonium intermediate is formed. Because of this bromonium intermediates, is a difficulty in the formation of this cyclic intermediates in these. The alkynes are less reactive than alkenes towards this electrophilic addition reactions. So once again, because of this difficulty in the formation of these cyclic intermediates during the mechanism, these are less reactive, that is, alkynes are less reactive towards electrophilic addition reactions than alkenes. So we can add two molecules of this halogen here. The first molecule adds to this, that is X2, that is halogen, any halogen. Here we are adding, resulting in the formation of trans dihalide, trans, and then one more molecule will add on to this, resulting in the formation of tetrahalide here. Let's look at the mechanism now. So because of this presence of this pi bond here, this adds on to this electrophilic addition reactions will take place, that is Br plus will attack, resulting in the formation of this cyclic intermediate, which is called a cyclic bromonium intermediate here. And in the next step, when the Br minus is adding, this is plus here, plus charge. When Br minus is adding, because of this cyclic intermediate which is present on one phase of the molecule, Br minus will attack from the other phase here. So resulting in the backside of the molecule, it will attack, resulting in the formation of trans dihalide here. So trans dihalide is formed because of the presence of the cyclic intermediate on the one side of the molecule. And then another molecule of this Br2 is added to this halide here, this dihalide. Again, the same mechanism follows, that is formation of the cyclic bromonium intermediate, and Br minus will attack in the next step, resulting in the formation of this tetrahalide here. So if we see this with the help of an example that we are uh, yeah, now let's look at this addition of hydrogen halides here, that is halogens we have done. So hydrogen halides, that is HX. This also undergoes the electrophilic addition of this HX. Alkynes will undergo this electrophilic addition with HX, similar to that of these alkenes. And When one equivalent of this one HCl is added, results in the formation of this vinyl chloride. Vinyl is nothing but the presence of the positive charge on the carbon, which is having a double bond here. So this is called as vinyl group. So this is vinyl cation. This is nothing but vinyl cation, or uh, this is called as vinyl cation. So this is intermediate which we are seeing during the mechanism of this process. So let's look at the whole picture of this first. So when one equivalent of this HCl is added, so this follows a Markovnikov's rules. That means the negative part of the addendum will goes to the carbon with less number of hydrogens. That is based on the stability of the intermediate, that is carbocation. Let's see that in the next slide. So Cl will go to the carbon with less number of hydrogens. So this will go to this carbon. So resulting in the formation of vinyl chloride, or that is nothing but alkynyl chloride. And in the next step, one more equivalent of this HCl can be added, resulting in the formation of geminal dichloride. Geminal means on the same carbon. So when this when this groups are present on the same carbon, it is called as geminal. Vicinal means on the adjacent carbons. Geminal means on the same carbon. So here the geminal dichlorides is formed again following the Markovnikov's rule. That Cl will go to the carbon with less number of hydrogens. So resulting in the formation of geminal dichloride. Let's see this mechanism now, how this will go on now. The first step is when HCl is added, so results in the H is added to the carbon here, which results in the formation of more stable carbocation. So when this hydrogen is going to the carbon here, with more number of hydrogens, results in the formation of a carbocation which is more stable. Here when the carbocation is formed here, it results in the carbocation, that is secondary carbocation, which is more stable. When the positive charge is developed here, it results in the formation of primary carbocation, that is vinyl carbocation, which is less stable. But here it results in the formation of more stable carbocation, so that the H will attack on the carbon with less number or more number of hydrogens. So this more stable vinyl carbocation is formed here in the first step, and then the Cl minus will attack this carbocation, results in the formation of alkynyl chloride following the Markovnikov's rule. So Markovnikov's rule is nothing but the negative part of the addendum will goes to the carbon with less number of hydrogens. This is with the less number of hydrogens based on the stability of the carbocation here. Yes, once again I repeat, so this process, this mechanism follows the Markovnikov's rule, which says that the negative part of the addendum will goes to the carbon with less number of hydrogens, following the stability of the carbocation. Here the secondary vinyl carbocation is more stable than the primary, so it is going through the secondary carbocation. So the Cl minus will attack this carbocation, that is which is having the less number of hydrogens, resulting in the formation of alkynyl chloride. And when the second equivalent of this HCl is added, again results in the formation of this carbocation, which is more stable here, which is more stable. The Cl minus will attack in the second step, and moreover this is stabilized by resonance also with Cl here, resulting in the formation of geminal dichloride following the Markovnikov's rule. Yes, when we see this with the help of an example here, for example, this propine, when added to this HBr, results in the formation of 2-bromopropene following the Markovnikov's rule. In the mechanism, if you see, this H will add to the carbon in such a way that it results in the formation of more stable carbocation, that is secondary vinylic carbocation, rather than the primary vinylic carbocation. If the charge is developed on this carbon, it results in the formation of primary vinylic carbocation, which is less stable. So this is not formed. So more stable secondary vinylic carbocation is formed. Then the second step, this Br minus will attack this carbon, resulting in the formation of this product, that is 2-bromopropene. Now let's look at this addition of water here. See, addition of water will take place, it's acid catalyzed. Also, again, the electrophilic addition will take place following the Markovnikov's rule in the presence of HCSO4 catalyst. So, this addition will take place and the mixture of mercuric sulfate in aqueous sulfuric acid is used as a reagent here for the addition of the water here, resulting in the formation of vinyl alcohol here. So this vinyl alcohol is in tautomerism with the keto form. So what is this? Let's see how this is formed and all this in this particular slide. Again, as I said, this is an electrophilic addition reaction which is taking place here. Yeah, when we see this mechanism, the addition of the water to this um, alkyne here, in the first step, the H plus will add in such a way resulting in the formation of more stable carbocation here. So the carbocation is this carbocation here, there's a vinyl carbocation. Then the second step, water will add on to this carbocation and followed by this deprotonation, that is H is removed, resulting in the formation of keto form, which is in equilibrium with the enol form. This is enol form here. This is an enol form which is in equilibrium with this keto form. This is an enol form which is in equilibrium with the keto form here. This is nothing but this equilibrium is called as keto-enol tautomerism. This phenomenon is called as keto-enol tautomerism or simply the tautomerism. There is this equilibrium. So how this equilibrium is formed is this bond will shift here and this one to this side, resulting in the formation of this keto form, that's the CH3C double bond OR. So because of the formation of the the shifting of the bonds here, this keto-enol tautomerism is can be seen here, this equilibrium, and the equilibrium is generally favors this keto form. Why? Because the C double bond, CO double bond is more stronger than that of this C double bond C. So this is more stronger than this C double bond C. So the equilibrium is more towards the keto form here. So this is what is keto-enol tautomerism, and the equilibrium lies more towards the keto form here.